Hello, I'm Tristan, and welcome to the CEA General Structure video. This video has a runtime of about 20 minutes. To begin, we should define exactly what we mean by structure. Now, if a greenhouse were just a big glass box, as it's often portrayed, this would be a simple definition. However, modern greenhouses incorporate many additional systems that are also technically part of the building. Heating and cooling systems will often be integrated into the floors or the walls. Piping, irrigation systems, and vents can run through the ceiling, as well as numerous other systems. In order to discuss structures meaningfully without making an impossibly long video, we therefore require a more precise definition. We define the structure of a greenhouse to be the parts of the greenhouse that do not expend significant energy in order to function. For instance, the steam heating system in the Cornell greenhouses, although definitely an integrated part of the building, would not be considered part of the structure, as it must actively expend energy in order to function. The windows, on the other hand, do not expend significant energy in order to function, requiring only the trivial amount of effort required to occasionally open and close them. So although windows could be considered part of the heating system, they are also part of the structure. We choose this definition because of how the greenhouse expends energy and what our goal is in the design of the structure. Despite how greenhouses are popularly conceived, their purpose is not to keep plants warm. Rather, their purpose is to keep plants in a given environmental stasis that is considered desirable for plant growth, requiring the greenhouse to eliminate both high and low temperature extremes. We represent this on a graph of temperature against time, where the straight line in the center is the greenhouse's desired environmental stasis. In reality, it will occasionally be desirable for a greenhouse to have different temperatures at different times in the day, but for the time being, this is an acceptable approximation. As the day goes on, the temperature will vary both above and below the desired level, requiring the expenditure of energy in order to return it to the desired environmental stasis. This can be the expenditure of natural gas or electricity to heat it, or the expenditure of energy required to run fans or other cooling systems. The area under this graph may therefore be thought of as a measure of the total energy expenditure of the greenhouse. And from an economic point of view, all energy the greenhouse expends costs money. Whether your energy source is natural gas or electricity or thousands of tiny hamsters on wheels, energy costs a certain fixed price per kilowatt hour. And so the more your greenhouse expends just to keep the desired temperature on a day-to-day basis, the higher your operating expenses will be. This tells us our goal for greenhouse structure design, as well as making it clear why we defined it the way we did. As the only part of the greenhouse that does not expend energy in order to function, the goal of the structure is to minimize the area under that curve, reducing the amount of active heating required to the lowest possible level. In order to do this, we wish to define a function f, which is equal to the area under that curve. It is an error function defined as the difference between the desired temperature and the current temperature taken over time. Once we have found this function, we can seek to minimize it, and from that find the most efficient structure design. Calculating the function f for any given structure design first requires data on the outside temperature over the structure's intended operating period and the desired interior temperature. Taking the exterior temperature as the default, that is, the function f when there is no greenhouse at all, we can then begin applying different factors and seeing how they influence the final outcome. For instance, in this graph, we have drawn a very basic example, wherein a classical glass greenhouse has been erected around the plants. Now, during the period when it is too cold, as you see in the center, this reduces the variable f. However, in this graph, the plants spend more time too hot than too cold, and so this is actually a net detriment to the efficiency of the structure. Catches like that are one of the most important parts of CEA structure design. A given system making the greenhouse hotter or colder is never inherently desirable. All that matters is that over the average desired operating period, it reduces the total energy expenditure. Although it is not easy to find, data on air temperature and sunlight in Ithaca throughout the course of the year is available, often gathered specifically for analysis such as this. Although crunching through all that data can be extremely difficult and is best automated, it is a critical part of efficient greenhouse design. In our example, we see that the greenhouse we're working with here is obviously in a very warm location, as it spends far more of its operating period too hot than too cold. We could decide to eliminate this glass framework entirely and simply enclose the greenhouse in sheeted plastic or some other method of protecting it from the elements. However, it does make it more efficient during the winter, and so we would prefer to find a way to negate the weaknesses of this feature rather than also eliminating its strengths. Looking through the list of other features we can add to the greenhouse without significant energy expenditure, we notice that extensive windowing does not significantly increase the price of the structure, but can always reduce it to the exterior temperature. We add this and change the graph to reflect this addition, finding that it significantly improves the efficiency of the structure. Earlier, we defined f as a function of multiple variables, but did not specify what those variables were. In looking at this graph, modified to reflect a glass enclosure with extensive windowing, you may notice that f can be defined purely as a function of the current outside temperature and of the desired temperature. This is not the case with all systems that can be added to the greenhouse structure. For instance, the performance of heat sinks depends not only on the current temperature, but on the previous temperature throughout various points in the day. Other cooling systems can depend on additional variables. For instance, the effectiveness of shading depends on how much sunlight the greenhouse is receiving at the time, which, while linked to temperature, is not the same variable. The effectiveness of other systems, such as evaporative cooling, can depend on technical factors, periods throughout the day, or other time-based influences. Combining all of these factors into one final function, f, is a task of non-trivial difficulty that becomes increasingly complicated the more design features are added. In order to simplify this task, rather than dealing with a function f that produces a temperature, we deal with a function we will call f sub q, which is the net rate of heat flowing out of the greenhouse at any given time. Assuming the greenhouse is at its desired stasis temperature, which during normal operation it should always be, f sub q should be equal to 0 in an ideally efficient case. The integral of f sub q over all time is therefore proportional to the integral of f over all time, and therefore we can seek to minimize f sub q as an equally efficient design goal as minimizing f. This simplifies our problem greatly, as f sub q can be taken as a linear combination of all of the f sub q sub n's that define each individual component. With this linearization in hand, we can see how we produce our final function f sub q. Although the effects of each individual system on the function f, as well as their interactions, are extremely complicated, their interactions on f sub q can be taken individually, and individually are extremely simple. This allows us to compute our final f sub q for any given design simply by combining the influence of each individual component and then examining the integral of the resulting f sub q function over our given operational period. And while that may sound like one long, terrifying sentence filled with math, it's actually extremely good. The ability to carry out a simple analysis of the effectiveness of any given component in influencing f sub q means we can automate this process, and once we have fully defined a given design, can simply plug it into a computer and have the computer spit out a final efficiency number. This ability to check our work is extremely important and will be revisited in greater depth in later videos. So far, we have only discussed how to calculate f sub q for known greenhouse designs, which presents us with a problem for designing new models. Since it's impractical to plug every possible greenhouse design into our fact-checking program to see which produces the best result, we are left with the problem of one-dimensional optimization. One-dimensional optimization is the method of finding the maximum or minimum of a function of multiple variables by finding the local minimum of the function for a given variable with all other variables fixed, and then assuming that when all variables are set to their local minimums, the overall function will be at its minimum. This method is inaccurate. However, under the circumstances, it is one of the only methods available to us. The way we have calculated f sub q, representing it as the sum of its individual components, eliminates the problem of the interaction between those components, rendering the problem solvable as opposed to the ridiculously complex derivation of the function f. However, this is only useful in one direction. Once we have a fully quantified design, we can calculate the effect of each component on f sub q